Okay, we are live. Hello, everyone. Thank you for joining us again uh, at this session brought to you by Oxford University Quantum Information Society. I am Hamza Wasim, Events Officer. And today our talk is about another interpretation of quantum mechanics called uh, the Bohmian mechanics, or the pilot wave theory. In the last few weeks, we had some introductory talks on many worlds interpretation and relational quantum mechanics. So I thought it would be very appropriate to have some representation of the pilot wave theory. And today our distinguished speaker is Professor John Brickmont. Professor John Brickman is a theoretical physicist who works on the renormalization group and statistical mechanics, but he's also interested in foundations of quantum mechanics, and he has written books for the lay audience and for students on quantum foundations. He has also written a book called Fashionable Nonsense, which criticizes the abuse of scientific terminology by postmodernist writers. And today he will be talking about the pilot wave theory. Over to you, Professor John Brickman.
Thank you. Is it okay like that? Okay, so thank you very much for the invitation of the Quantum Information Society, even though I won't speak about information, but hopefully about the world. So let me start very slowly with things that most people know, namely start with a quantum property which is archetypical of quantum properties, namely the spin. And let me start with pure phenomenology. It's a variable that takes two values in any given direction, up and down. Consider two directions, label 1 and 2. And so you can have spin up and down in each of these directions. And there also exist devices that measure the spin in direction 1 or 2. I mean, this is purely symbolic, of course. There is a box here that measures the spin direction 2. If you feed in the box particles that are up in direction 1, then if you repeat the experiment many times, half of the particle will go to this hole for the 2 up, and therefore the 2 down. And here it will be, if you put 2 up in a box that measures direction 1, then you will get the same 50-50 sort of result. And that's the same thing if you started with 1 down or 2 down here. Now put 2 boxes next to one another. And then the first surprise is that if you take the particles that are spin up in one direction and you feed them in a box that measures the spin direction 2, and remember you started with particles that are spin up in direction 2, then you will get again 50-50, while you would expect naively that maybe since the particle were 2 up there, they will all be 2 up here, but that's not true, they're 50-50. So after being measured in direction 1, the particle seems to have forgotten that it was 2 up to start with, up in the direction 2 to start with. Now, one thing which is impossible to construct is a box which would measure simultaneously 1 and 2 and would have 4 exits, one for those that are up both in 1 and 2, up in 1 and down in 2, and the 2 other possibilities. That's an example of what Bohr calls complementarity. You can speak of one property, the spin being up or down in direction 1 or in the other direction, but not both simultaneously. That's also a version of indetermination relation of Heisenberg. Now let's go to interference effect, and let's consider the Maxender interferometer. So you put particles with spin down in direction 1 in a box that measure the spin direction 2, and then those that exit, which are 2 up, go there, those that are 2 down go there, and then there's a mirror, they're reflected, and then they recombine here, and I explain in a minute what happens here. But let's say that you start with 2 up rather than 1 down. So the 2 up, the 2 up will all go in that direction, they will all go in that direction, and then when you measure in direction 1, of course you will get 50-50, because that's exactly what you will have if you measure the 2 up to start with, and this part there just doesn't change anything, okay? And of course, if you start with 2 down, you will have, if you started with 2 down, all the particles will follow that path, and here you will have 50-50, 1 up and 1 down. But if you start with 1 down, then 50% go this part, 50% go that part. You could detect them. But then somehow when you recombine them, there's a way to recombine them so that we measure in the direction 1 now, you get 100% going in the direction down. That's a bit strange because I just told you that after being measured in direction 2, particles forget that they were 1 down or 1 up before. But now they actually remember. After having this little trip there, they remember, and you have 100% 1 down. Now insert a wall along the path. That will block half of the particles, so here we'll have only 50% of the original particle. And then you will, of course, after the wall, the problem is that before, you see all the particles that took that path ended up being 1 up, 1 down when you measure in direction 1. But now that you put this wall, the thing which is somewhat surprising is that now those particles get again 50-50, namely 25-25, since this is half and half of the 50% remaining. Okay, so without the wall, 100% of those that take that path end up going down. But after the wall, the same for those who take the other path. But if you block the 1 down, it seems that it could not affect particles that take that path. Since they were all up, down, one down after here, I mean, in that experiment, they were all down here, you would say, well, putting a wall here should not affect the result, but it does. So you act in a certain way on the particles that take one path by blocking the path that they do not take. That's another surprise of this thing. And then it will look like you are at a dead end, because if you take this experiment where they end up being 100% down, what does the particle do? Does it follow this path? Well, no, because otherwise you would expect 50-50 after the arrow, since when you force it to follow one path, it's 50-50 after the arrow. And path down, not for the same reason. Both paths, no, because you always find the particle along one of the paths. Neither of the two paths, no, because if you block both paths, nothing happens. So that's the first quantum mystery. Another version, which you certainly know, is the double slit experiment, which is advertised by Feynman mostly, but that's better known. You have a hole here, you send electrons. If you block one slit, one hole, then you get a distribution like this. Of course, this is an average distribution, but every electron is sent one by one, and they record it one by one, and this curve just represents the statistics of these detections, okay? So now, of course, and if you take both holes, then instead of having the sum of these two curves, you get this wiggly line, which is an interference pattern, and which is what you would expect if instead of having particles, you would have waves, okay? And these sort of interference pattern, you see it again here. So the quantum mathematical solution is very simple. You represent state by vectors in C2. Doesn't matter that it's complex, but I don't use complex number here. And using Dirac notation, one up is represented by this vector, one down by this vector, two by this and that, and they're represented graphically here in real space. And then, of course, you can check that two up is a linear combination of one up and one down, and two down also, etc., the whole combinations of the other. And the rules of quantum mechanics is a state evolves outside of measurement the following way. The state is a function of t, a coefficient depending on t times one up, plus a coefficient depending on t times one down, or the same thing in the basis 2. And of course, you can use this change of variable, change of basis formula to go from one to the other. These coefficients change in time. Let's say that's Schrödinger equation or a similar equation. At all times, the sum of the square is conserved. It's equal to 1. Before, we had 1 over square root of 2 for all of them. And the evolution is linear. Namely, if at some time say 0, you have the state is a combination of these two states. Then at a later time, you will have a combination, the same combination of the state evolved from 1 to t, state 2 evolved to state 2 to t, and the evolution is also deterministic and continuous in time. When a measurement is made, that's the second rule, so there are two rules. One rule is the evolution outside of measurement. If we measure the spin direction 1 and the state is this, the result will be 1 in probability C1 square and down with probability C2 square. And of course, the same thing if you do in direction 2, except it will be with d1 square and d2 square. Okay. After the measurement direction 1, if you see up, so you see, for example, that, then the state collapses to that state. So it's no longer a combination, it just jumps to that state. And of course, if you see down, it jumps to the other one. And the same thing for measurement direction 2. This operation is called the collapse of the reduction of the state. It's incompatible with Schrödinger's evolution. It is nonlinear, discontinuous in time, and non-deterministic. What about the wave function? Since you have heard something about quantum mechanics, you probably have heard about the wave function. Well, it's a function psi of a variable x, which is the position, like the spin, has value in r instead of having two values up and down, or in a multidimensional space. And psi is just a function whose integral square is normalized and equal to 1, and the Schrödinger evolution preserves that. So you can interpret these numbers now as the density of probability to find a particle at x if you measure its position. It's very important to realize that quantum mechanics only speak about what happens if you measure the position. It doesn't tell you that the particle is there before you measure. It just tells you that if you measure, that will be the density probability, the probability density of finding the particle. Okay? So how does that work in the Maxender experiment? Well, now I've represented by disk the support of the wave function. So the wave functions come here. It's split into two parts because there is the spin up in the direction 2 and the spin down. And they follow this path and they bounce against the mirror and they go there. And so at the initial time, the one down is a superposition of 2 up and 2 down. In between, it becomes a function which is 2 up times the spatial part would be path 2, which indicate path 2 up, namely the path here. And here would be the path down, which would be the path here. Okay. And these are just the wave function. They're represented by disk. This is very, very, very idealized. And at T4, what happens is you have to recombine both wave functions. So you get the original this and that combined to a path which goes in that direction. And then since those two guys are combined, this is the same vector as 1 down, as we see from here, and 1 down times the path there means you have 100% down. If you put a wall on the other hand, this is a measurement, so it collapses the state. And after the wall, but time-wise, if you look at this guy, then the state collapses to 2 up, path 2 up. And what it arrives here is a combination of, 2 up, so that combination of 1 up and 1 down, and therefore after the arrow, you get 25% up, 25% down. And here you see the whole of measurement, namely doing a measurement here will affect the behavior of the particle that take this path. You have two mutually incompatible rules, one about what happens outside of measurement and one about what happens during measurements. The problem posed by this duality of rule was expressed ironically by Bell. It would seem that the theory is exclusively concerned about results of measurements and has nothing to say about anything else. What exactly qualifies some physical system to play the role of measurer? Was the wave function of the world waiting to jump for thousands of millions of years until a single cell living creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? Now there are basically, I think you can list the reactions to that problem. There are 4 different reactions. One is saying that physics deals with measurements and nothing else. That's how I understand basically what Copenhagen is saying, and a modern version is what is called cubism. That, in my opinion, confuses the means and the ends. As again, I will often quote John Bell, experiment is a tool. The aim remains to understand the world. To restrict quantum mechanics to be exclusively about piddling laboratory operation is to betray the great enterprise. The serious formulation of quantum mechanics will not exclude the big world outside the laboratory. I may be even more critical by saying that when you ask the government to give you taxpayer money in order to do expensive experiments, you tell them, oh, we are discovering the laws of nature, the secret of the universe, etc. And then when you go to your philosophy of quantum mechanics seminar, you say, well, there is no world outside the laboratories. We're just predicting results of measurement. But then if you tell the government that all you want to do is amuse yourself to predict results of measurement, you won't get the money if they understand what you say. So there is a basic problem of honesty here. The second reaction, which is the one I used to believe when I was younger, is that if you analyze measurements within the quantum theory, the problem will be solved. Then there's a third thing, which is a very natural interpretation, which says that measurements reveal pre-existing properties of the system, and the quantum state gives the statistical distribution of those properties. This, I think, when you discuss with the no-worry physicists who say, well, who cares, there's no problem in quantum mechanics, I think implicitly there's this view, not often explicitly. And the fourth one, which I will, of course, defend, is look for another or more complete theory. So let's go to solution 2. So you want to analyze the measurement within the quantum theory. So what happens there? Well, consider a very simple quantum system composed of the spin of a single particle, and I neglect the wave function. So I have my usual spin up and spin down with some coefficients here. The measuring device, I reduce it to a pointer, which is initially in the original position. And at the end, it's either pointing up or down, depending on whether the spin has been measured up or down, okay? In order to describe the measuring device quantum mechanically, because I want to do everything within quantum mechanics, then I have to associate with a quantum state. Let's call phi 0 of z the initial wave function associated to the pointer, with phi 0 of z centered at 0. So phi of z corresponds to this picture in the figure, okay? And let's consider an initial state, which now will be the phi 0 of z times this combination of up and down. Okay, that's the total quantum state of the measuring device and the system. Consider first another initial state corresponding simply to the particle being spin up. So I take only that part, and C1 is put to 1. Since the pointer will go up if the spin is up, the final state will be what I denote by phi up of z times the vector 1, and that corresponds to the pointer being as this in this direction. So this is phi 0, and this is phi up. If I start with the particle being down, I will get phi down, and phi down corresponds to this picture. Okay? Now, what happens if the initial state is this combination? Since it's a linear combination of two other states, and since evolution is linear, the final result will necessarily be this combination. And that means that it's this represented by this picture. It's a sum of being upward and being downward. But concerning the pointer, you can only interpret this state as being a superposition of two different macroscopic states, not state or spin, which we don't know what it is, but macroscopic state. One where the pointer points upward and one where it points downwards. The problem is that this does not at all represent the state of the measuring device as we know it. The pointer is either upward or downward, not a superposition of both, or if you prefer, the complete description, because sometimes people say quantum mechanics is a complete description of the world, then the measuring device, the complete description, is certainly not a superposition, since a more complete description can be obtained simply by looking at the result. The problem is that measurements are well-defined results, and the quantum formalism does not account for this fact. Of course, you could say that if I, for example, I throw a coin and then it falls on the table and I put my hands on the coin, don't look at the results, then of course, could be similar to this. You could say, well, you know, the probability of being heads and tail is 1/2, but then of course, you know that the coin is either 1/2 or either up, either tails or heads. You don't say the complete description is that probability. And here we have something similar where you insist that this is a complete description. To make the situation more dramatical, but without changing anything to the issue, you can couple the apparatus to a cat. That's a very famous experiment by Schrödinger. You imagine a cat and a mechanism that will link the pointer position to a hammer that breaks the vial of poison. If the pointer is oriented in one direction, does not break it, is in the other direction. The vial is broken, the poison kills the cat. Okay, and then the state of the cat is this famous cat alive plus cat dead, which again doesn't make any sense because we know that the cat is, I mean, many people think that the cat is both alive and dead, but that's not, certainly not justified by anything. Now, it is sometimes suggested that the problem mentioned here is solved by the fact that it's impossible to produce interference effect between the state of the pointer oriented upwards and the one oriented downward, or the cat alive and dead, comparable to effects that occur in the Maxender experiment or in the double slit one. And this is true, and it's called decoherence, but it does not solve the problem, namely that quantum mechanics does not account for the uniqueness of outcomes, the pointer being up or down, but not both. What decoherence implies is that when observe the pointers being up or down, one can use that state, the one up, and forget about the other one in order to predict the future behavior of the system without risk of making mistake. That's true, but it doesn't solve the conceptual problem, namely the central role of the observer, because what you have to do is observe the pointer in order to know which state to use. Now consider solution 3, which is the very natural solution. If it works, it would be beautiful. The statistical interpretation. Measurements reveal pre-existing properties of the system, and the quantum state gives the statistical distribution of those properties. So a state like what I have here, C1 and this combination, would mean that among the particles having that quantum state, a fraction of them would actually have their spin up, and a fraction of them would have their spin down, C1 square and C2 square, respectively. And you see, that would mean that there is secretly, I mean, even though the state here, the state would not be a complete description. The particle will, on top of them, have this hidden variable, as it's called, some property that tells them that in an experiment, they will go up and they will go down. So you have a statistical interpretation, and the state gives the statistics of that. So if you want to formalize this idea, you associate to each individual system a map that gives for each observable, like the spin, the hidden value that this observable has in that individual system prior to any measurements. These values are called hidden variable because they are not included in the quantum state. The latter would simply, in the statistical interpretation, give a probability distribution over those maps. This interpretation is a way to complete the quantum formalism. If that worked, there would be no mystery in the reduction operation. It would just be like when I have my coin on the table, I lift my hands and I look if it's head or tail, then I learn something about the system and I change my probability distribution. I learn the coin was either head or tail before I look. By looking, I learn something about the system and I update my probabilities accordingly, which is what could be more natural than that. The only problem with that is that the map V does not exist. Now, the only part here, which is a little bit mathematical, and you have to trust me because this is a purely algebraic result. It's clever, but there is nothing physical, no physical assumption whatsoever. The fact is that it's a theorem due to originate with the help of Gleason, Koch, and Specker, were mathematicians, also by Bell. There is no map from a set of matrices which represent physical quantities like the spin. I didn't discuss the spin matrices, but they are matrices representing the spin quantity, such that the value of A is an eigenvalue, the value of A is an eigenvalue of that quantity, and when they commute, the value of the product of the values. Now, these two properties are simply properties which are satisfied by result of measurement. This property that they commute means that they can be, A and B can be simultaneously measured. Unlike the spin in one direction, the spin in the other direction, I told you that you cannot build a box that measures both, but for certain quantities, you can build a box that measures both simultaneously, and the result must satisfy that. On the other hand, the result must also be eigenvalues of A, and there is no such map. Okay, so the morality is that you cannot have a probability distribution on things that do not exist. And that's the end of the statistical interpretation. So the summary of the quantum mystery is the statistical view, which is the most natural in my view, is untenable. The measuring devices have an essential role in the quantum formalism. They reduce this reduction, but the latter cannot be understood as merely revealing pre-existing properties of the system being measured. Measurement do not simply measure, they in some sense act on the system. But how? In ordinary quantum mechanics, they're a pure deus ex machina. Doesn't explain how it acts. Only a more detailed theory can explain how they act. But now forget about everything I've said and think about a much deeper problem than the problem I've already listed, what I call the existential angst. Am I a vector in a Hilbert space, which is in part simply a function defined on a high-dimensional space? What about you? You feel you're a vector in a Hilbert space? In reality, before, when I spoke of phi up of z and phi down of z for describing the pointer, they are not function of one variable, in fact, but of all the coordinates of all the particle or point in the pointer or in the cat. The main problem, is not that psi cat alive and the superposition of psi cat dead, the superposition of the two states, but that the psi cat alive alone or psi cat alone, they are not cats. They are abstract mathematical objects. They are not objects located in R3 like cats or pointers or you or me. And that's a bigger problem, which is, well, I didn't invent it, but it's massively overlooked, even by critical of the Copenhagen interpretation like Einstein and Schrödinger. I didn't see that they were mentioning that, but maybe they did, but okay. But the point is that usually people take for granted, they identify this abstract mathematical object and a concrete object in three dimensions. But there is no justification for that. once you think about it, it's quite obvious that only quantum mechanics cannot be the complete story. It does predict results of measurement, but does not say anything about what is going on in the world. What we need to say something about the world, namely we need an ontology. We need to postulate something that exists outside of laboratories and that is not just the quantum state. We need an ontology that includes more than the measuring devices, because if you are instrumentalist or Copenhagen, and so on, you have an ontology that are just measuring device and you don't know why we did the measuring device in the first place. But it must be also less than the values of all the observable, because the no hidden variable theorem tells you that you can't do that. By the way, this is the main problem of the pure many-world interpretation. The pure many-world interpretation, the world is this abstract mathematical object. There is no ontology, only an abstract mathematical object called the quantum state. Hence, I will summarize it in a slogan: many worlds without ontology equal zero world. Now, I get to my point. It's the theory of the Broglie-Bohm. I call it like that because it was introduced by de Broglie in 1927, or even before that, even in 23, 24. And it was presented at the Solvay conference in 27. Then it was abandoned by de Broglie for bad reasons, but it was then rediscovered by Bohm in 1952. Bohm gave the complete theory, and I say and Bell because Bell did a lot to advertise it. But of course, there is also work of Dürr, Goldstein, and Zangi, and many other people who have developed and advertised the theory. So what I want to say is the theory of hidden variable, although they are not at all hidden, as we will see. Excuse me. That account for all the phenomena predicted by ordinary quantum mechanics, that is not contradicted by the no hidden variable theorems of Koch and Specker and so on. And that explains why measurements do not in general measure pre-existing properties of a system. In other words, it explains why measuring devices have an active role as Bohr and company wanted, but just made it into a postulate. So let's think of the double slit experiment I already explained. So one slit, you have this, one slit and two slits. And then usually you say, well, when one slit is open, electrons are particles, both slits are open, they're waves. And then the poor electron has to figure out whether it's a wave of a particle before reaching the first wall. And people make a lot of mystery about it. How can they be both particles and waves? Elementary, my dear Bohr, they are particles guided by waves. What could be more simpler than that? Particles guided by waves. In the de Broglie-Bohm theory, the state of a system is a pair. It's not just a wave function. It's a pair where for a system of n particles, there is a vector x1, xn that denote the actual position of all the particles in the system, and psi is the usual quantum state. And x1, xn are just the argument of the function. They are not, you should not confuse the big letter and the lowercase letter, because these are just the argument of psi, and these are the actual position of the particle. X are the hidden variable in this theory, but it's a misnomer since particle position are not things that we ever observe directly. If you take the double slit experiment, these curves represent an average of dots here, and each dot detects one particle is sent at a time, and you detect one particle on this wall. Okay? The dynamics, I will not spend a lot of time on dynamics, I will basically deal with pictures, but on the one hand, you have Schrödinger's equation, and strictly speaking, the quantum state never collapses. It's a bit more subtle than that, but this is just the usual Schrödinger equation, which you learn in quantum mechanics courses. And then there's the guiding equation, which again, I won't go too much into it, and I give the simplest form. The velocity of the particle, the first derivative of the position, the particle as a function of time, is a function of the wave function. This is constructed from the wave function. So the way you think about it is that the Schrödinger evolution evolves the wave function, and then the wave functions guide the motion of the particles. Okay? By the way, the particles, unlike what you have been told, have position, they have trajectories, they have a velocity, etc. And this is not contradicted by anything, any empirical fact, and certainly not by Heisenberg uncertainty principle, but I won't go into that. Now think of the double slit experiment. Here is the numerical solution in the de Broglie-Bohm theory. Now each line, each of these wavy lines is a trajectory of a particle, which you could go there and see its initial condition here. So you send particles, some of them come to this hole, some to that hole. And of course, we can't distinguish initial condition here, but each initial condition gives rise to one of these lines. And you see that here, there are many particles, and here there are few particles, and this will correspond to the interference pattern. Notice that the motion is a motion. It's just a dynamical system. but it's not classical. Why would you like it to be classical? The first law of motion of Newton is not satisfied because here you are in vacuum. There's only the wave function which acts, but there is no potential, if you wish, no force. But the motion, okay. Now, of course, I don't have pictures with only one hole, but if I had one hole, if this one was blocked, the motion would be very different. Because the particle goes through one hole, but the wave, because the wave goes through both holes, and therefore affect the motion of the particle that goes through that hole. Nothing more be simpler than that. A wave, of course, like a water wave, sound wave, etc., will go through both holes. Note also that you can determine a posteriori to which hole the particle went. It usually say you can't do that, but actually the theory tells you that you can do that. But what you cannot do is, of course, measure behind the hole through which hole the particle went, because that would affect the wave function, would affect the future behavior of the particle. In fact, if you block that hole, you would have more particle coming through that hole and going down here than you have in this situation. Notice also that there is what you call another line, namely there is a line in the middle here that particle cannot cross, and that allows you to tell you which hole you went through. Okay, now I just mentioned in passing an experiment, but I won't go into detail, which is done with photons and which has a picture which looks qualitatively like this one. Then again, to quote Bell, he says about this experiment, is it not clear that from the smallness of the scintillation on the screen, since you detect a particle one at a time here, that we have to do with a particle? And is it not clear from the diffraction interference pattern that the motion of the particle is directed by a wave? De Broglie showed in detail how the motion of a particle passing through just one of two holes in the screen could be influenced by waves propagating through both holes. And so influenced that the particle does not go where the waves cancel out, but is attracted to where they cooperate. The idea seems to be so natural and simple. To resolve the wave-particle dilemma in such a clear and ordinary way, that's a great mystery to me, that it was so generally ignored. It's a great mystery to me too, by the way. Now, let's answer two questions. One is, how does the Broglie-Bohm theory account for the statistics, the quantum statistics, and how does it deal with the spin and the Maxender experiment, etc.? Okay. So why do you get the predictions of quantum mechanics? First of all, you must realize that in any deterministic theory, any statistical prediction must come from assumption on the initial conditions, statistical assumption on the initial condition. Think of classical statistical mechanics, think of dynamical system, chaotic dynamical system, think of simply throwing a coin or a dice. I mean, the result is random, but of course the initial condition must be random in the same way. There must be some randomness. So when you repeat the experiment many times, you don't control the variable very precisely, so you have statistics. So if the empirical density of particles at some initial time, by that I mean this, in this simple picture, I have a certain distribution of particle. If the distribution of particle, that's the empirical distribution. If it coincides with psi square at the initial time, then this is the trajectory, the Bohmian trajectory in a very simplistic way. And after time t, the empirical distribution here will coincide with the distribution at the later time, with the wave function at the later time. So you will get the empirical distribution initially is psi square, and at the later time it will be psi square. That empirical distribution comes from the guiding equation, and this function Schrödinger equation. That's why it's called equivariant, because they vary together. Okay, so that means that, of course, if you assume that rho 0 equals psi 0 squared at some initial time, then it will hold at all times, and it will reproduce, of course, the statistical predictions, at least for the particle position. Okay. So the assumption that rho 0 is psi square is the quantum equilibrium. Now, this is a very natural assumption, but I can't go into that in detail. Okay, I mean, it would be too long to discuss it, but I can assure you that this can be considered natural. In any case, some assumption must be made on initial condition in order to account for statistics in a deterministic theory, because the theory is a dynamical system, it's completely deterministic. Now, what about the experiment with spin and the Maxender experiment, etc.? Okay.
Sorry,
so here
John, would you like to take a question?
Okay.
Okay, so Lawrence Frolov asks, The guiding equation is not unique. By this, I mean the same quantum predictions can be made using an alternate guiding current by adding a term with zero divergence to the continuity equation. Bohmian mechanics usually takes the extra term to be zero. Is there a way to experimentally test which guiding equation expresses reality?
No.
If not, is this an argument against Bohmian mechanics?
The answer is no to both. I mean, there is underdetermination in Bohmian mechanics. But I agree, okay, no, that's true. You can have different guiding equations. I took the simplest one. But my philosophy is that even, you see, there is a sense in which reality is hidden from us. We don't know, for example, we can't know, we can't reproduce the position of the particle. When you do many times the same experiment, you get different position. And then we can't even know what the exact trajectories are. But the fact that you can think in terms of trajectories, you can think in terms of a deterministic equation, that's really the message of the Broglie-Bohm theory. And you can recover the quantum predictions. That there is no unique way to do that, well, that's life. It doesn't bother me so much. I mean, if there was a unique way, I'd be happy. But I will go later, I will come to this question about predictions. I want to show you that we recover the usual predictions, and then I will explain what it means and what I think about what it means, okay? So, but it's a good question. And the answer is that indeed it's not unique. But the answer is that it doesn't bother me also very much. I mean, it bothers me a little bit, but not much. So let's start with interference. So here I have the wave function that I had in the one down, and then there's a part that goes up and a part that goes down, and then a part that goes down. This should be well, it should be, anyway, there's a mistake here with the 2, but anyway, so that should be 2 up actually. But anyway, at T1, you have this superposition, and then you have the wave function as I discussed before. And now I've put a little dot, a black dot or a white dot, which represent the position of the particle. So you could, of course, they are not sent simultaneously. Once you send the black goes this way, and the white goes this way. And then when they recombine, they always go in that direction. Because the particle is always guided by the part of the wave function support of which it finds itself. So the particle is here, what matters is this wave function. The particle is there, what matters is this wave function. But when we recombine the wave function, then the recombined wave function guides the particle. And then we get that as the wave function will all go in that direction, the particle will also go in that direction. So you detect 100% one down. Good. Now if you put a wall, that will change the wave function. After the wall, at T3 after the wall, you will get only that part. And if the particle, of course, the particle goes there, you don't hear about it. So assume the particle goes here, that's the black particle. When it arrives here, the particle will be guided by the wave function here, but that part will be absent. So it will be just this part. And then it will be again a superposition of one up and one down. And when you do the measurement in one, you get 50% of 25% if you wish of each possibility. If you combine both waves, you get different results than if you block one of them. That was also the case in the double slit experiment, because in the double slit experiment, you had the wave going through one hole influence the particle even though it goes through the other hole. And here, of course, the particle is influenced by whether the wave here reaches this part as in this experiment, or whether it does not because of the wall here. The fact is that the wave function here is physical because of its guiding property. It has a physical meaning, it's not simply a probability amplitude. Finally, my last point is, why do measurements other than those of position do not in general measure the pre-existing property of the particle? Remember, I explained the no hidden variable theorem that says you cannot think of measurements as simply revealing properties of particle. Now consider a Stern-Gallach apparatus, which is one of these boxes, the more realistic way to show these boxes, which I described in the beginning, that measure the spin, and let's particle being a superposition of one up and one down, and here it's a magnetic field, and the gradient of the magnetic field is in that direction, and therefore the particle, the wave function will split into 2 parts, one going up, one going down, okay? Now you start with a particle, the one part goes in the direction of the field and the other goes in the opposite direction. Now you start with a particle over here, And because the particle is the upper part of the support of the wave function, assuming again this is this little disk, then it will always go up for a symmetric wave function. That's because in this experiment, again, there is a line in the middle that the particle cannot cross. The fact that it cannot cross has very strange consequences. So it's exactly like here, there's this another line, okay? Because repeat the same experiment with the direction of the field reverse and assume that the particle starts with exactly the same wave function and the same position as before. Now, because of this line, it will have to go up again. But going upwards now means going in the direction opposite to the one of the field, since you have reversed the notion, the direction of the field. So the particle whose spin was up will have its spin down, although you measure exactly the same quantity, the spin in one direction, with exactly the same initial condition for both the wave function and the position of the particle, but with two different arrangements of the apparatus. So that's where the apparatus plays a role. Whether you put the field in this direction or the opposite, the particle will be up or down, even though it will always go in the same direction, precisely because they're always in the same direction. Now you can show using invariance that the statistical prediction for the spin measurements are the usual one, assuming quantum equilibrium. So you recover the usual quantum prediction for the spin measurement, just as for the position, but no intrinsic property of the particle is being measured, and that's the same thing for other so-called observables, which are not really things that you measure. Therefore, the apparatus does not register something pre-existing to the measurement. It's not a property of the particle. The particle here does not have a value, a pre-existing value of the spin either up or down. But it plays an active role, and this vindicates the intuition of Bohr and others about the role of the measuring device, but it makes it a consequence, a mathematical consequence of the theory, and not some philosophical a priori. It is usually the orthodoxy that adopts a naive realism with respect to operators. The only thing we ever see are particles' position, and the calculus with operators allow us to compute the statistics of those positions in certain types of interaction which are misleading called measurement. So you should not speak of measurement, but of interaction, and the statistics of the result of those interactions are given by the quantum formalism. But that does not mean that one has measured an operator, assuming that this expression makes sense. The summary is that the main virtue of the Broglie-Bohm theory is that it's a clear theory about what's going on in the world, whether we look at it or not. So the vagueness and subjectivity of the notion of observer or measurement simply disappear in this theory. The theory, and that's my point about, makes the same empirical predictions as ordinary quantum mechanics, and you presented it as saying that it's an interpretation of quantum mechanics. It's not, because they are not the same theory. One is a theory about the world. Ordinary quantum mechanics is not. It's an algorithm for very accurately predicting results of measurement. An algorithm that is in fact a consequence can be deduced from the Broglie-Bohm theory. So the Broglie-Bohm theory is a completion of quantum mechanics. It's not an alternative, it's not an interpretation. You don't interpret, you don't try to make sense of the formalism, you complete it. If you wish, ordinary quantum mechanics is truncated Bohm theory, and since it makes the correct prediction, you don't need to worry about it at all, unless you start thinking about what does it all mean, and then you get into all kinds of trouble. Once you know the Bohm theory, then you don't have any question about what it all means. Okay? But of course, it doesn't help you in any way. So using the Broglie-Bohm theory, one can easily explain why all the arguments that are supposed to prove that such a theory is impossible are false. I'm sorry. Why deterministic, the Broglie-Bohm theory also accounts naturally for the apparent indeterminism of quantum phenomena because of initial condition. It explains, I just said, the active role of measuring devices, the apparent effect of observation on reality, so strongly emphasized by the Copenhagen people, but it makes it a consequence of the theory and not of some a priori philosophical doctrine. And then the usefulness, thanks to the Broglie-Bohm theory, one gets rid of entire library of bad idealist philosophy, of mysticism, the role of consciousness on the world, confused statements that students repeat without understanding them, of ill-defined main world theories, etc., etc. Other than that, the Broglie-Bohm theory is useless. That's not completely true, because many people use the Broglie-Bohm theory in order to compute the statistic, the wave function in certain situations, but that's not my field. And then I will finish with one more quote by John Bell after recalling the arguments claiming to show that a theory such as the Broglie-Bohm is impossible. 1952, this is the year I was born, by the way, I saw the impossible done. It was in paper by David Bohm. Bohm showed explicitly how parameter could indeed be introduced into non-relativistic wave mechanics with the help of which the indeterministic description could be transformed into a deterministic one. So what he means by the parameters are, of course, the position, the trajectories of the particle. More importantly, in my opinion, the subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated. And then he says, should the theory not be taught, not as the only way, but as an antidote to the prevailing complacency, to show that vagueness, subjectivity, and determinism are not forced on us by experimental facts, but by deliberate theoretical choice. Then I mentioned, of course, my book, which is not the only one on the subject, but it's a book which I think is relatively elementary and where you can find answers to, I think, most of the questions. Of course, there are many other books. There is the Jürgen Teufel book, there is the Dürr-Goldstein-Zengi book, there is a book by Moldin, there is a book by Norsen. I didn't list the whole story, but anyway, so, okay, thank you.
Thank you so much, Professor John Brickman, for this thought-provoking talk. I have a question about the state of the art of Bohmian mechanics. Critics of Bohmian mechanics say that it's very hard to extend it to the level of quantum field theories, or much needs to be done in that direction. But what's your take about this?
Okay, I expected that question. And okay, I don't know you, and maybe you know everything about Bohm in ordinary quantum mechanics. But usually I get this question as a put down. You see, why should I bother with your theory since it doesn't work in quantum field theory where everything is fine? Okay. Well, first of all, the short answer is that there is a quantum field, a Bohmian quantum field theory. There are several. The only problem is that several of them, there is more under determination when you go to quantum field theory than even for non-relativistic quantum mechanics. That's a real problem, if you wish. And then there are problems with relativity, which I can discuss, but that's not I don't think it's a real problem in my view. But usually people say that, you see, just to get rid of it. Don't bother me with this theory. Why, if you think about all the debate between Bohr and Einstein and Pauli and von Neumann and all the Schrödinger cat, etc., and even Bell's experiment, and all these things took place within non-relativistic quantum mechanics. And non-relativistic quantum mechanics is really, as Bell says, 95% of physics. Okay, so it seems to me that if I come with a theory, even though I would have no idea whatsoever about quantum field theory, and I give a complete solution of the non-relativistic quantum mechanics, but it takes a few hours to really understand it, I think it would be worth, if you are interested in understanding what physics is about, to understand non-relativistic quantum mechanics. And I'm not talking about you, but I was sure I would have that question, so I prepared the answer, because the question always comes to sort of get rid of it, okay? It doesn't work in quantum field theory. And it's repeated all the time. It's not true, because in the 52 paper by Bohm, he discusses quantum field theory. And there are lots of papers by Dürr, Goldstein, Zengi, and Watt-Strehl. There are many other people who have written papers on quantum, quantum field theory, Bohmian quantum field theory. Kumulka, I mean, lots of them. So what are the problems? Well, there are two sorts of problems. One is under determination. Do you have a quantum field theory with only fields? Do you have a quantum field theory with particles? If you have a quantum field theory with particles, is it deterministic or not, etc.? Okay, these are questions on which I'm not an expert, but it's true that there are different theories, and you have an underdetermination problem, which was already mentioned in the previous question, namely you don't know, whether it's going to be, what it's going to be. Is it going to be, which version of the theory is the true one, and you don't have access to reality in order to tell which one is the true one, because many of them will make the same predictions. Okay, now there is a problem of relativity. Usually people say, well, it's not relativistic. Well, certainly non-relativistic quantum mechanics, Bohmian mechanics is not relativistic. But then people say the theory is intrinsically non-local. By non-local, if you look at the equations, maybe I should go back to the equation. the guiding equation, you see, depends for one particle, for the kth particle, on the position of all the other particles. So by acting on one of the other particles, I can change the wave function, and therefore I can affect the behavior of this particle. And that's intrinsically non-local. And that was a problem, and certainly Einstein didn't like it, and many other people didn't like it. But my view is that Bell has proven, and there are many other proofs of that, that the world is really non-local. So the fact that the theory is non-local is a quality rather than a defect, because if it was local, then it would be contradicting by Bell aspect experiment, Bell theorem, whatever. That would be a whole other conference, which I'm willing to give whenever you invite me again, if you feel like, but I can't explain it in detail, but the short answer is that the world is non-local. So there is a problem with relativity, irrespective of what you think of Bohm. And I think Bohm, the non-locality of Bohm is a quality rather than a defect, because any empirical theory of the world must be non-local.
Yes, agreed. Now there is a question about your opinion on the lack of back reaction of the particle on the wave. So the wave guides the particle according to the theory. Is there back action?
Well, not really. Yes and no, because there is a, okay, the particle position does not act on the wave. But of course, the material content of the universe determine the potential that are in the Hamiltonian, and of course the Hamiltonian acts on the wave. You see, if you have charged particle, then you will have a potential, but the potential will not be related to the position of the particle. It will just be there in the Hamiltonian. But you see, my view on this is that if we have been told for so many years that we should give up the notion of reality, then why do you care if there is back action or not? Okay, I mean, it seems to be such, okay, the theory is like that, it's a theory. Is it empirically adequate? Is it mathematically well defined? If it does that, then it's to be considered and it should be analyzed. And whether there is back action or not, I don't see, is there back action in ordinary quantum mechanics? There's no, I mean, just because, you see, the problem is, as I said, the trajectories are highly non-classical, because where is first laws of motion of Newton? Well, it's not classic mechanics, it's just not. So, you know, that's the way it is. I think the philosophy I have for me is to take it as it is and try to analyze it. I don't see why you say, well, maybe you should have back action, maybe not. I have no opinion about that. I mean, you could say, you see, is there back action of particles on the Hamiltonian in classical mechanics? Well, it's not entirely clear what you mean by that. It's more, you can think of the wave function as the Hamiltonian, if you wish, in some sense, okay? You could think of the guiding equation like one of the Hamilton's equations, Schrödinger equation as the other Hamilton equation. I mean, it's an analogy, but you could make that analogy if you want.
Right. There's another question. What motivates looking for a microphysical ontology in Bohmian mechanics in the first place?
What's the motivation?
Yes, for a microphysical ontology. I don't know what microphysical means here, but
because I believe that things are made of atoms and atoms are made of particles. I would like to understand what goes on with the particles. It's reductionism, if you wish, but I think that's what we always do, no? I mean, we have always done that in physics. And if we can, of course, if we are told we cannot do it, and there have been tons of arguments, including the Noether variable theorems and von Neumann, God knows what, showing that it cannot be done. Okay, but that's what Bell says. In 1952, the impossible was done. And if the impossible is done, then I'm happy about it. If people say you shouldn't look for it, why shouldn't we look for it? Why don't you want to have it? The explanatory, take statistical mechanics and thermodynamics. You don't need statistical mechanics to do thermodynamics, and engineers who use thermodynamics don't bother with statistical mechanics most of the time. But are you going to tell me that statistical mechanics is not an advance relative to thermodynamics? Well, it's the same thing here. You could say that thermodynamics is the quantum formalism, and Bohmian mechanics is the statistical mechanics underlying it. It's an analogy which is valid. Now you can say you don't care, but you don't care, you don't care. You don't have to be a physicist also. I don't know. I mean, you can be an engineer and be happy. As I say, the nice thing about Bohm is that it clarifies everything. It just gets rid of all this bad philosophy, mysticism, and so on the one hand. And on the other hand, it doesn't bother you because you don't have to do any more calculation. If you don't want to, then the Schrödinger equation, because the predictions don't go beyond the Schrödinger equation, you cannot control the individual trajectories. And so you go back. So it's exactly what the doctor ordered, namely you get an understanding of what's going on in the world, which just completes quantum mechanics and doesn't make quantum mechanics either wrong or doesn't force you to do more calculation than you usually do. It's perfect. It's perfect. But of course, if you say I don't care, but you don't care, you don't have to care. Why do you care? Why do you have to care? No.
The next question is, I think, a very common misconception about Bell's theorem. So the question is, if Bohmian mechanics need hidden variables, does it not make contradiction with Bell inequality?
No. Because that's the subtlety. Bell inequality, well, first of all, you have to understand the complete reasoning. Since I'm not sure you will invite me again, let me give you in a nutshell what Bell showed. What Einstein, Podolsky, and Rosen say, which is universally misunderstood, they basically say that if you take this entangled pair of particles and you measure the spin in one direction on one side, then you automatically know what the result will be on the other side because they will be anti-correlated. Okay? So basically what they say is that there must be hidden variable pre-existing instruction, if you wish, on those particles that tell them what they will do, or else you have an action at a distance, namely measuring on one side will affect the result on the other side. Okay? And that was the dilemma. They didn't put it as a dilemma because non-locality appeared to them totally crazy. So they say there must be a hidden variable that tell the particle what to do, because if I measure on one side, then the other particle knows what to do. And how could it know what to do if there is no action at a distance, if it didn't know what to do before the measurement on the first side? Okay? So that's what EPR did. And then Bell simply showed that this hidden variable did not exist. But the point is that in Bohm, as I explained, the spin hidden variable don't exist for reasons I've explained. And if you do the EPR experiment a la Bohm, then you see exactly why doing a measurement on one side will affect the result on the other side. You can, it's detailed in my book, but in many other places. And, then it's exactly very, very natural. I mean, nobody in the no hidden variable theorem has ever said that you can't introduce position. And that's all you do. It's interesting also when you speak of velocity, momentum measurement. I can't go into that in detail, but if you take a particle, that was a problem that bothered Einstein. If you take a particle in a box or in the ground state of the harmonic oscillator or most ground states, the wave functions are real. And if you remember, I said that the velocity is related to the gradient of the phase of the wave function. Of course, if it's real, then S is 0, the gradient is 0, and the particle is at rest. So the particle in the box, the particle will be at rest. Nevertheless, if you measure the momentum, you will get the Fourier transform of the wave function, get a non-zero result. Then you can ask, how can that be true? Well, the fact is that if you measure the velocity of the particle, you must remove the boundaries of the box and let the particle evolve. And then if you compute the asymptotic velocity, you find exactly the correct prediction of quantum mechanics, starting from the initial distribution of particles at rest. So when you measure the position, actually the velocities, you act on the particle, and therefore you don't get the initial velocities, but some object which is a velocity, which is the one predicted by quantum mechanics, but it's not the original one. So there is no contradiction between particle having a position and a velocity, and having measurements of velocities that do not coincide with discovering the original velocity. You don't discover. That's an example where the particle does have a property, but when you measure it, you don't discover that property with something else. So that's again a subtlety of the measurement in Bohmian mechanics. But it seems to me that the Bell experiment is totally, very naturally explained inside Bohmian mechanics. And there's no contradiction at all. The contradiction would be if I introduce hidden variable of spin, but I don't.
Right. Next, we have a question by your friend, Abdul Afzal. He says, it's
a friend of?
Your friend, Abdul Afzal.
Hello.
Yeah, so he says, Bohmian mechanics seems to add to quantum formalism guiding equation, but we get less out of it. It forces one to take a neo-Lorentzian view of relativity, which is controversial, and if trajectories are fundamental, then it marries us to take the view that space is fundamental as well. Whereas predominantly in quantum gravity, research seems to be shifting towards theory of quantum gravity, which aren't embedded on a background metric. Where does that leave Bohmian mechanics?
Nowhere, because I don't know what quantum gravity is to start with. I mean, Abdul seems to think he has a theory of quantum gravity. I would like to see it and then give him the Nobel Prize, but I don't know what is exactly the theory of quantum gravity. I don't think you should put the cart in front of the horse. I mean, the point is that to object to a theory which is trying to explain everything about non-relativistic quantum mechanics, which can deal with usually quantum field theory, and then say, oh, but it doesn't go for quantum gravity. Just wait and see. Let's have a full-fledged theory of quantum gravity, and then we'll see what we can do. I think what Strev has worked on Bohmian mechanics for related to gravity. I don't know these things very well. I'm not an expert on that, but it seems to me that this is an objection, which again is a way to put down things and say, don't bother me with this theory because it doesn't work in some far-fetched thing. By the way, about quantum field theory, people are very strange because they think everything is fine with quantum field theory. And they think of actually of field, they have hidden variable of field. They think they are field configuration. They say the field fluctuates and blah, blah, blah. But when it comes to particle positions, they say, oh, the particles don't have position, they don't have trajectories, etc. But when they speak of fields, it's exactly the same thing because the fields are to field theory what particles are to non-relativistic theory. So if you don't have particles, they don't have position, etc., the fields have no position either. So all these hand-waving things about fields fluctuating and gravity fluctuation and so on, it's not at all clear what it means. Plus, I think that if you speak of relativity and you speak of relativistic quantum field theory, then I challenge you to find one book, because I didn't check all of them, of quantum field theory, where even in the index, there is a mention of words like reduction of the wave function, collapse of the wave function, and so on, so all the quantum state, etc. So when you learn quantum mechanics in the first course, it's an axiom that you have reduction when you measure blah, blah, blah. And then when you do quantum field theory, you don't mention it anymore. What you do study indeed is scattering cross-section in the end. That's fine. And it's remarkable. But where is the quantum theory? Where is the axiom of collapse? And why isn't there an axiom of collapse? Well, that's simple, because the collapse is, again, something happening at a distance instantaneously in the EPR experiment. And it's very hard to deal with that in a relativistic way. In fact, I think it's impossible in the usual way of thinking about relativity. And therefore, people don't mention it when they do relativistic quantum field theory. But their quantum field theory is not really relativistic because it doesn't even account for the simple EPR experiment. So let's not put the cart in front of the horse, Abdul. Just write down your quantum gravity and then we'll see how to go on about it.
Okay, so my next question is about the acceptance or the lack of acceptance of Bohmian mechanics nowadays. Do you think do you think people still are, people still are doing shut up and calculate, and they don't think that they need to understand quantum mechanics better, or are there some other forces at play?
Well, that's of course more a question about sociology than about physics. Yeah. But as all representative of minorities, either religious or political or whatever, or philosophical, I will always reply that my minority is increasing. But that's not certain. But I think, you see, when I was a student, it was really unmentionable. The main professor in my university, when you ask him about quantum mechanics, he replied with a heavy Swiss accent, because German Swiss accent, Bohr has explained it all. And he never explained how. So this thing that Bohr explained all, shut up and calculate and so on and so forth, this was the dominant mood when I was young. I think this has changed. I think there are more and more young students who are there to ask questions. My problem is that there are too many, I think, undefensible answers, like many words, GRW, etc. But okay, there are at least people ask questions. That's already a progress. And I think that now we have books at every level. There is a more technical book like Dürr and Teufel. There is a more physics books like the one of Travis Norton. There is a philosophical books by, Maudlin, and there is a sort of book with all the articles by Dürr, Goldstein, and Zangi, and so on. There are many books at all different. And my book, which is at the intermediate level, so there are books at different level. And I think there was not. It wasn't so easy. I mean, there was the beautiful, absolutely extraordinary book of Bell, about speakable and unspeakable. But people don't read it because people don't understand. People say Bell has shown that knowledge and variable theories don't exist, but he defends the knowledge and variable theory, for God's sake, throughout his book, namely the Broglie-Bohm. He explains it. But Bell writes in a very condensed way. So if you miss the point, you will miss it. And I think it's good that there are many more pedagogical explanations. There are articles by Shelley, Goldstein, and what is called the Stanford Encyclopedia and so on. And there are articles about Bell also by him and others. So there are many, now it's very, if you want to learn the theory, it's very accessible. Before, especially when Goldstein and Zangi tried to explain, the quantum statistic, quantum equilibrium, and what they call the effective waveforms and so on, that was, of course, difficult to figure out, but now that's sort of explained in many different ways. So I think if you want to learn it, you can learn it very easily. If you don't want to learn it, you don't learn it. That's your choice. You don't have to bother with that. But if you are bothered by quantum mechanics, I suggest that you learn that, because that's a very simple, it's a very natural way to explain these things and to answer all the questions that can be asked, again, that are asked within the context of non-relativistic quantum mechanics, and then you can go a step further and think about quantum field theory, relativity, and so on, but then you have to understand Bell and so on and so forth, and that's the next step. But what I've explained here, which is the basics, is something which I think is interesting to understand. If you're interested in understanding what the physics is about, if you just want to do computation, I say the beauty of Bohm, it doesn't force you to do any other computation. If you have GRW and you have collapses, then you have a different theory. It makes different predictions. You adjust the parameter so to avoid having refutation by experiments so far, but it's a different theory. And if it's true, then means quantum mechanics is false. And then, of course, there should be some parameter for which it's true. We don't know which ones. And okay, I know that's the only theory which I can make sense of. Many worlds have many objections, which I won't go into now. But I don't think, for the reason I mentioned, that there is no ontology, then I don't understand what it means.
Okay, I think I'll ask the last question for this session. Are there any state-of-the-art experiments which could, reject or help bring some support for one or two of these interpretations?
No, of course not. And that's the beauty of the Broglie-Bohm. There is no, because I keep on saying it's a completion. It explains what ordinary quantum mechanics does. It's not a different theory. But ordinary quantum mechanics restrict the theory, which is the Broglie-Bohm, to prediction of experiments. The algorithm to predict results of measurements is a derivation of quantum mechanics. Okay? It's like if you are saying the statistical mechanics show that thermodynamics is wrong. No, but it, of course that's not exactly a good analogy, because there are experiments that go beyond ordinary thermodynamics and statistical mechanics. That's true. But to me, it seems to me that the whole theory, the quantum mechanics, is just the Broglie-Bohm. There's nothing else. And then you can restrict yourself, and then you get into all kinds of problems, because what is this wave function means, and what does the measurement mean, and what about these two rules, and so on and so forth. And you can go on and on worrying about these things. You should worry about these things, but there you have an answer. But you're never, I hope, you're not going to have an experiment that determine which one is right, because the quantum mechanics is doing so well. So it's good that something that I think Dr. was telling me once. I mean, when they were working on it, the first question they were asking is, how do we recover the quantum prediction? Because we need to recover the quantum prediction. The theory is so good. Now, if you have GRW, for example, spontaneous collapse theory, then they make different predictions. But then they're clever enough to adjust parameters so you can't observe them. But that's not exactly something I find appealing, but stricto sensu, if the theory is true, then quantum mechanics is false, and there should be experiments telling you which is which. And if that's true, then quantum mechanics is false and Bohm theory is false. That's fine, but it has not been proven so far. And I think this insistence that people have this sort of positivistic state of mind that they say, well, if they make the same prediction, then same theory. No, because it's a theory about the world. If I give a wave function, if I take an electron here, and I say, here is its wave function, it's a quantum state, or several of them. And I ask you, what does it mean? The only honest answer you can give is to say, if I bring the guy in the laboratory and I do this and that experiment, then I get this and that result with this and that probability. That's the only honest answer. You cannot tell me what the quantum state means outside of the laboratory. But I believe there are electrons in the room. Yeah, I believe you believe that too. And but then they have a wave function. But then the wave function, as I say, the only way you could do the statistical interpretation, that would make sense, but it doesn't work. Bohm is a statistical interpretation, if you wish, that does make sense because it only introduces position and then derives the statistics of all the other observable and all the quantum formalism from the behavior of those positions. So I think that's, can't have it better than that, I think.
All right. On this note, we will finish this session. Thank you so much, Professor John Brickman.
Thank you very much for
giving us your time.
It was a pleasure to discuss and to answer the questions, and I appreciate all the questions and the opportunity to speak, to give information to the Information Society.
Thank you so much. We'll invite you hopefully in fall next time for another talk,
Okay.
maybe on a more advanced level.
If you wish.
Bye. Bye, everyone.
Okay, so